Good morning. In today's class, we'll learn about the asymptotic notations, big O, omega, and theta notations. So, we'll start with the asymptotic notations. Let us take two algorithms A and B to solve a problem, and TA and TAN and TBN be the executing time for a given value of n. The algorithm which takes less time to execute has to be considered among A and B. In the last session, we learned that efficiency of the algorithm concentrates on the growth of algorithm's basic operation count. But running time of an algorithm is usually measured in by considering the behavior of the two functions, asymptotic behavior of the two functions. So asymptotic behavior is always considered for a very large value of n, which means that asymptotic notation is nothing but the performance of an algorithm in terms of input size. We calculate how does the time taken by an algorithm increases with the input size. How does the time taken by the algorithm increases with input size is considered as the asymptotic analysis. It refers to computing the running time of an operation in mathematical units of computation. This is asymptotic notation or asymptotic analysis. In simple words, if we have to say that, it is the performance measurement of the algorithm with respect to input size. As the size of the input is increased, the time taken by the algorithm also increases. This calculation or mathematical representation is called as asymptotic analysis. The time required by an algorithm falls under three types: best case, average case, and the worst case. Best case is the minimum time required for the program execution. Average case is the average time taken by the program execution, and worst case is the maximum time required for program execution. There are basically three asymptotic notations: big O notation, omega notation, and the theta notation. First, we'll start with the big O notation. Let f of n be the time complexity of an algorithm. The function f of n is said to be big O of g of n, denoted by, you can see here the function which I have written here, f of n is equal to big O of g of n, which is written as f of n is equal or belong to big O of g of n. This is the representation. Now in this diagram you can see there exists a positive constant c and a positive integer n naught satisfying the constraint given below. Constraint is f of n less than equal to c of g of n for all n greater than n naught. So what is big O notation? It is a formal way to express the upper bound of an algorithm's running time. Nothing but it measures the worst case time complexity, or the largest amount of time the algorithm can possibly take to complete. So big O notation is nothing but it is the formal way to represent maximum time taken by the algorithm. For maximum time is nothing but worst case. And if we draw the graph f of n and c of g of n versus n, the graph f of n lies below the graph of c of g of n for sufficiently large values of n as shown in this diagram. You can see in this diagram This notation is used to denote upper bound on a function within a constant factor. The upper bound indicates that function f of n will not consume more than the specified time c of g of n. That is, the algorithm has a running time that is always less than c into g of n for large value of n. This is about. Next we move on to the omega notation. Let f of n be the time complexity of an algorithm. The function f of n is said to be big omega of g of n, which is denoted by the equation as shown here. F of n belongs to big O of g, omega of g of n, which is read as f of n is equal or belong to big omega of g of n, such that there exists a positive constant c and non-negative integer n naught satisfying the constraint f of n greater than equal to c into g of n for all n greater than equal to n naught. And if we draw the graph f of n and c of g of n versus n, the graph f of n lies above the graph of g of n for sufficiently large value of n as shown in the diagram. This notation gives the lower bound on a function f of n within a constant factor. The lower bound on f of n indicates that function f of n will consume at least the specified time c of g of n. That is, the algorithm has a running time that is always greater than c of g of n. In general, the lower bound implies that below this time the algorithm cannot perform better. And the notation omega big omega is the formal way to express the lower bound of an algorithm's running time. It measures the best case time complexity or the minimum amount of time the algorithm can possibly take to complete. Next we have theta notation. Let f of n be the time complexity of an algorithm. The function f of n is said to be big theta of g of n, denoted by f of n belongs to theta of g of n, or f of n is equal to theta of g of n, such that there exists some positive constant c1 and c2 and non-negative integer n naught satisfying the constraint c1 into g of n less than equal to f of n less than equal to c2 of g of n for all n greater than equal to n naught. So if we draw the graph f of n, c into g of n and c2 into g of n versus n, the graph of f of n lies above the graph of c into g of n and lies below the graph of c2 into g of n for sufficiently large value of n as shown in the diagram. This notation is used to denote both lower bound and upper bound on a function f of n within a constant factor. The upper bound on f of n indicates that function f of n will not consume more than the specified time c2 into g of n. That is, the algorithm has a running time that is always less than c2 into g of n for large value of n. The lower bound on f of n indicates that function f of n is the best case. In the best case, will consume at least the specified time c1 into g of n. That is, the algorithm has a running time that is always greater than c1 into g of n. And theta notation is the formal way to express both the lower bound as well as the upper bound of an algorithm's running time. So asymptotic notation is nothing but it is the mathematical representation of performance of the algorithm with respect to input size. And we classify the asymptotic notations into three types: big O notation, omega notation, and theta notation. Big O notation is used to express the worst case time complexity, the largest amount of time the algorithm possibly take. And omega notation is used to measure the or express the, it's a formal way to express the lower bound, that is the best case time complexity. And theta notation is used to measure average time complexity of the algorithm.